Okay, I hope you can hear me, no? And you can see my screen. Am I audible?
Yes, sir.
Okay, so we will do. Okay, so today we need to learn some basic discrete time signal, discrete time signal. Okay, I think in signal and system one we have learned about uh, continuous time basic signals. Okay, basic signals. Maybe you can remember. Okay, the first one we have learned is uh, unit impulse function delta t. Okay, the second one is the unit step function ut. The third one is complex exponential minus j 25 ft. Okay, so e plus j 25 ft and sinusoidal. Okay, so I'm only referred as cos 25 ft plus 5. Okay, so we have learned these four basic signals. I think you can remember. These are continuous time signals. Okay, so this is a unit impulse signal. Okay, this is unit step signal. This is complex exponential signal. This is sinusoidal signal. Can you remember that why these are called basic function or basic signals? Can you answer that question? Why these are called basic signals? Actually, it is because we can represent other signals. Okay, we can represent other signals, other arbitrary signal. Okay, any signal, arbitrary signals using this function. Okay, that is why we call this. These are basic signals. Okay, I think you have that idea. Maybe we have represent. I think you can remember that we have represent some signal in complex exponential terms in Fourier series and Fourier transform, and also we have represent some signal as a collection of sinusoidal function, no? As a collection of complex exponential function, no? As a collection of sinusoidal function. Okay, so that is from Fourier series, Fourier analysis. I think you can remember that one. Okay. So in the same manner, these signals are also, this unit impulse signal and unit step signal also can be used to represent other signals. Okay. So that is the basic idea. You should have that one. Okay. Now we have to learn the discrete version of these signals. Okay. We have to learn the discrete version of these signals. Okay. Actually, we are mainly focusing on unit impulse signal, unit step signal, and sinusoidal signal here. Okay, not exponential signals. Okay, so we will discuss. Okay, first we try to uh, try to refresh our previous knowledge. Okay, so I think it is better to use the reference book directly. So I will take that from. Mhm. Some wait for a moment. Yes. Okay. So this is our reference book. Okay. So always you have to refer this one. Okay. If you have any problem, you have to refer this one. And if you can't understand the content, you can ask the help from me. Okay. Okay. So here in the first chapter, okay, basic continuous time signal. Okay. So we have learned these things. Okay. Uh, yeah. So first we have learned the unity step function. So it is like this. Okay. This is the unity step function. Okay. This is the unity step function. Okay. Okay now. Ah, this one. Okay, okay. Okay, this one. Very good. Mm, okay. So this is the unity step signal. Okay. So it is like this. Okay. So so you can see that it is just like a DC signals, no? DC signals is starting from here. Okay. For example, if you take a function generator, signal generator, sorry, the power supply. Okay, power supply. If you set the power supply voltage to some level, let's say that 2 volt. Okay. And if you connect, if you, this is the plus and minus probe. Okay. If you connected the resistor something here, the voltage between this resistor is a constant voltage. Okay. Like this, 2 volt. Okay. And I think you can see that for a normal DC signal, the minus part also can be there. Okay. Minus part also can be there. Okay. But in the unity step signal, this minus part is not available. Okay. The only plus part is available like this. Okay. So if you, let's say, if you, let's say that you have a signal generator and you have a switch here. So I will write it here if it is not clear. So this is our power supply. Okay. Now you have set the voltage of this power supply to 2 volt. Okay. And you have the plus probe and the minus probe. Okay. So if you connect the switch like this, okay, and if you connect any load, okay, if you switch on this, if you switch on this switch at t is equal to 0, okay, so between this load, you will have 2 volt constant voltage, no, constant voltage. So if you have plot the voltage with respect to time, okay, so you will get this kind of function. Okay. So this is very much similar to the unity step signals. Okay. Unity step signals, you can see that. Okay. But here the value is 1. Okay. So if you, so this, if you want to do the two, okay, so you have to wait on this. Okay. So if you have put a weight, okay, so for example, this can be represented as 2 UT. Okay. This can be represented using 2 UT. So you have put 2, weightage of 2. Okay. So like this, you can represent this kind of signal using a unity step signal, unity step function. Okay. DC signals. Okay, but if it is a DC signal, okay, remember that if it is a DC signals, normally the minus part is also there. The minus part also there. Okay, but for the unit step signal, minus part is not available. Okay, is it clear? ඒක ක්ලියර්ද ඔය කට්ටියට? If you have any problem, please ask. Okay, if you can't understand, you can ask me, then I can explain it again. Okay, and this is the shifted unit step function. Okay, so we are applying the time shifting techniques here, time transformation techniques. I think we have learned uh, three type of time transformation: time shifting, time reversal, and time scaling. Okay, so if we apply the time shifting techniques, okay, we can shift this unit step function. Okay, so this is the this is shifted unit step function. Okay, okay, so to get more clear, I will give you one simple exercise. Okay, so let's say that you have a voltage pulse, okay, like this. Okay, let's say that this is T naught and this is T1. Okay, this is T naught and this is T naught. Let's say that here it is 2 volt. Okay, so this is a voltage pulse. Okay, this is a voltage pulse. This is a voltage pulse. So can you try to represent this using shifted unit step function and unit step function? Okay, using shifted unit step function, and this is the shifted unit step function and this is the step function. Using these two functions, can you represent these signals? Can you represent this signal? So take 5 minutes and try to do this. Tell me the answer. Okay, so you have to write this pulse using these two. Okay, ut and ut minus 2, ut minus t naught. You have to write using these two signals. Can you do that? I think we have done this in signal and systems. If you can remember, I have done this. Try to represent. Okay, I will do this one. Okay, okay. So you can understand that T naught, the T1 is greater than T naught. No, I think this is okay because this is just like 2 seconds. This is just like 3 seconds or something. Okay, because the time is going to this way. Okay, so definitely T1 is greater than T naught. Okay, okay. So now what you have to do is, okay, so if I draw the unit step signal, okay, the shifted unit step signal u t minus t naught. If this is minus, okay, the function is shifting to this way. If this is plus, the function is shifting to this way. Okay, so this is the time delay shifting. If it is shifting to this way, we called it delay shifting. And if it is shifting to this way, what is we called? What have we called it? It is a time advance. Okay, it is an advance shift. Okay, so here you have a delay shift. Okay, ut minus t naught delay shift. Okay, so if I write u t minus t naught. Okay. So my signal is shifting to this way by t naught. Shifting to this way by t naught. Okay. So I have this kind of shifted unit step function. Okay. So I think this is okay. Then if I draw u t minus t1 function, okay, so it is also same, okay, but you know that t naught is greater than t1 is greater than t naught. If this is 2 second, t1 is 3 second, okay, so it is shifting to somewhat this way, okay, it is shifting to much longer than this one, okay, so you have this kind of method. Okay, so if I write it together, those two signals, okay, let's say that this is T naught and this is T1, okay, U T minus T naught, I have like this, okay, then, so this is T naught, this is T naught, and this is T1, okay. Now, if I draw U T minus T1, okay, I will have like this, okay. So this is from here, this is from here, okay. Now you can see that in this pulse, you have only this portion, no? From T naught to T1, okay. So here we have only this portion, T naught to T1, this portion, okay. So if you want to get this portion, only this portion, what we have to do? Tell me that one. This is ut minus T1, okay. Ut minus T1, okay. So if you want to keep this portion, what you have to do? Tell me that one. If you want to now, you want to keep this portion. So what you have to do? You have to, you in this function, you have values from here to here. In this function, you have values from here to here, no? The first function, ut minus t naught, you have values from here to up to plus infinity. And in ut minus t naught, you have values from t1 to plus infinity. Okay. Now you have to keep only these values. Okay. And you have to get rid of these values. From t1 to plus infinity, you need to get rid of from these values. So what you have to do? Please tell me what you have to do. I think it is very simple. තේරුණාද මං හපේ? දැන් අපිට ඕන මේ සිග්නල් එක ලියා ගන්නනේ. මේ සිග්නල් එක මෙන්න මේ කෑල්ල කොහොම හරි යුනිට් ෆන්ක්ෂන් වලින් ලියා ගන්න එක. යුනිට් ස්ටෙප් ෆන්ක්ෂන් වලින්. හරි? ඒකට මම ගන්නවා ඉස්සෙල්ලාම ගන්නවා ut minus t naught unit step function shifted unit step function එක ut minus t1 unit step function එක. දැන් මේ ෆන්ක්ෂන් එකෙන් තේරෙනවානේ t1 විශාලයි කියලා t naught ට වඩා. t1 තමයි ලොකුයි. හරි? දැන් අපිට ඕන t naught ඉඳන් t1 ට වැලියු ටික. මෙන්න මේ t1 ඉඳන් plus infinity වලට යනකල් values ටික අයින් කරගන්න ඕන. එහෙනම් මොකද්ද කරන්න ඕන? What you have to do? What you have to do? For example, here maybe you have 2, 3, 4, 5, 6, 7 like this. Okay. Let's say that T naught is 2 and T1 is 4 or something. Okay. So you have 2, 3, 4. Okay. And 4, 5, 6, 7, 8, 9 like this. Here also starting from 4, 5, 6 you have. Okay. Now you need to reduce this. You need to get off this 4, 5, 6 values and you have to keep from 2 to 4. What you have to do? You have to subtract, no? You have to subtract this value, these values from this value. Okay, here you have 2, 4, 5 like this. Okay, and here you have 4, 5, 6, 7 like this. Now you want to get rid of these values. Okay, so what you have to do? You have to, if you have subtract these values from these values, what happen? This 5, 6, 7 you can get rid of, including 4. Okay, then you have only you can get up to 4 values, no? Okay, so if I subtract this, u t minus t naught from u t minus t1, I have only the values from t naught to t1. Okay, like this. Okay, but here the value is 1, no? Because this is unit step function. The values, the weight is 1. Here also the weight is 1. So this weight also will be 1. Okay. Here this 2 means I write the T naught value. Okay. This 2 and 4. Those are T naughts value. Okay. T value, time value 2 and 4. Not the amplitude values. Okay. The amplitude is 1. Correct? The amplitude is 1. The time values I have right. Don't get confused. Okay. These 2 and 4 are times values. Okay. So you will have this kind of pulse. Okay, but the weight is 1. Okay, but you are given 2-volt signal. No, you are given 2-volt signal. So you have to make this 1 to 2. Then what you have to do? Okay, so if you have multiplied this by 2, if you multiply this by 2, you will get the given signal. No, if you multiply by this one and this one, okay, so you can separately multiply it. T naught minus Tu T minus T1. Okay, then you will have T naught T1. This is 2. Okay, so this is how we represent a DC pulse or DC signals using a unit step signal. Okay. Okay, now as exercise, try to do this one. Okay, now no need to you do. Okay. So in the interaction session, if you can't do this, you can ask me. Okay. This T. Okay. Let's say that here you have 2 seconds. Okay. And this is 1 volt. Okay. And here you have 3 volt. 3 volt. Let's say that this is 4 and this is 6. Okay. So this is your signal, voltage signal. This is 1 and this is 3. This is 2, 4, 6. Okay. Now try to represent this using shifted unit step functions. Okay. As a collection of shifted unit step function, try to represent this one. Okay. So I think now you can do it. Okay. So this part you can represent using 2 unit step function. For example, u t minus 2 minus u t minus 4 You can write this one. And this one you can write as ut minus 4 minus ut minus 6. Okay. And it should be multiplied by 3. Then if you add those two functions, you can get this one. Okay. So that is how we can find it. Okay. So very easy. You can find this. Okay. Try to find this. Okay. Okay. Now that is, so I think now you can understand how we can use the unit step function to represent this kind of signals. Okay. Okay. Now, okay. Now, actually, any signal you can approximate as this kind of, so this is we called staircase function. Okay. This is we called, these functions are called staircases function. Okay. So any signal you can approximate to this kind of staircases function. For example, if you have a sinusoidal signal like this, so you can represent it like this. Okay. It is not completely correct. Okay. But you can get the shape, no? Okay. So this is like this. Okay. So you can see that this approximated staircase function, you can represent using unit step function, shifted and weighted unit step function. So these signals, this signal you can represent using this one. Okay. Okay. So that is how we can use unit step function to represent other signals. Okay. So that is why we called it the basic function. Okay. Now let's move to the unit impulse signals. Okay. So if I take the reference book, I will take that one. Okay. Okay. And unit step function is like this. Okay. Here T, and you have like this. You are representing like this. Okay. And we called it 1. So this 1 is the area of this line. Okay. So there is a line from this 0 position. Okay. From this 0 position, there is a line. And we have put arrow. That means this line is goes up to the infinity. Okay. And here we mention 1. This 1 means the area of this line. Okay. So you can see that if you get very small one, okay, small one, okay. For example, if you take this kind of a rectangle, okay, if this is 1 and this length also 1, okay, 1 by 1, the area is 1, no? Okay. And if you take this length 0.5, then you have to take this length 2. Again, it is 1, no? Area is 1. And if you take this length 0.25, and if you take this length 4, again it is 1, no? Okay. Likewise, if you take very little width, you have to take very high width, very high height, big height to make this area 1. Okay. Make area 1 කරන්න ඔකට ලොකු height එකක් තෝරගන්න. So now if the width of this 0, okay, to become to make the area 1, you have to go this length up to infinity. Okay. So that is why we represent the unit step, the unit impulse signal like that. Okay. So width is 0, but area is 1. This width is 0. This width is 0. But the area is 1. So if the width is 0 and area should be 1, it should goes up to infinity. It should be very high value, very big height. Okay. So that is why we put the arrow here. Okay. So this is completely mathematical function. Okay. This is not a practical function. This is completely mathematical function, and also it is mathematically complex. Okay. It is not a simple function. It is very complex, complicated function. Okay. And it is defined like this. Okay. So actually here we are taking the integration. Okay. Here we are taking the integration means we are taking we are measuring the area. Okay. For example, if you have a function like this, t, like this, okay. Let's say that this is xt, okay. And if you take the integration from this to this, let's say that this is t1, t naught to t1, t naught to t1 xt into dt. So you will get the area here. This is the area of this function, okay. So here also you are calculating the area. You take the delta t function, you take the delta t function, you select any values, okay. You select any values. So, so it can be minus infinity plus infinity, it can be a to b, okay. Here it is measuring minus infinity, minus 5 to 5, okay. So if you integrate with respect to t, you will have 1, okay. So this is the area, okay. So this is the definition, one definition. And also this is another definition, okay. So if any function is multiplied by the unit step function, and if you integrate it from minus infinity to plus infinity, you have the value 0, 0. That means, okay, so that means if you have this kind of function, okay, and if you have multiplied this function from the unit impulse function, this function, and you have integrated uh, over this function, okay. If you integrate this over this function, you have only this value, phi t. This is the phi 0 value, this value, okay. So you will get this one, okay. And the shifted version is like this, okay. Shifted version is also like this, okay. And actually this one you can, this definition you can represent, you can use to represent any function using the unit step function by shifted unit impulse function, okay. But don't worry, okay. I'm not going to ask to do that one because it is somewhat complicated, okay. But you can see that this is just like xt, okay. So xt naught is equal to minus infinity plus infinity xt delta t minus t naught, like this, okay. So xt also can be represented as a collection of shifted delta t function, okay. Continuous shifted delta t function like this, okay. But don't worry, okay. If you can't completely understand this, it will be okay, okay. Because here we are not going to focus on this continuous impulse, unit impulse function, okay. We are not focusing on continuous unit impulse function, but we need the discrete unit impulse function. Discrete unit impulse function is somewhat simple than this one, continuous one, okay. It is somewhat simple. This is not simple, this is complicated. This is mathematically complex, okay. But if you consider the discrete unit impulse function, it is not mathematically complex. You can understand it very easily, okay. So anyway, if you can't understand this completely, it will be okay, okay, no issue, okay. Then this is the complex exponential function. You can represent it like this, okay. So it is like this, it is increase in signal, and this is the minus exponential signal, so it is a decrease in sinusoidal signal, okay. So this is the Euler formula. I think you can remember, we have used this one, okay. So the complex exponential signal can be represented as two real and imaginary sinusoidal function, okay. Okay. Actually, here we are not in DSP, we are not going to much discuss about the complex exponential signal. So you can provide this one also. Okay. And this is the sinusoidal signal. Okay. So you can represent it like this. Okay. We have learned this one. Okay. So this is sinusoidally changing. Okay. So this omega naught is angular frequency. I think you can remember it. This omega naught is angular frequency. This is angular frequency. Okay. And if you want to find the normal frequency, you can write it as 25f naught. Omega is equal to 25f. Okay. And this theta is the phase shift and this A is the amplitude. Okay. So here you have that one also. Okay. This one. Okay. So sinusoidal signal is like this. Okay. So these are continuous time signal. Actually, we are mainly focusing on these discrete time signals. Okay. So we are mainly focusing unit step sequence. Okay. And unit impulse sequence. We are not, we no need to go through this one. Okay. Complex exponential sequence. Okay. We will avoid it. Okay. And we have to learn the sinusoidal sequence. Okay. So we have to learn these three type of discrete time signal. Okay. Okay. Now we will do it. Okay. So anyway, if you need a short break, take around 5 minutes. Okay. And we will meet at 5:05. Okay. So then we will start to learn this discrete time version. Okay. Okay.